Yeah. Hi, everyone. I'm Hanyan. For those of you who don't know me, I'm responsible for hosting the journal clubs at UC Quantum. And it is my pleasure to introduce Rick Yoon, who's a rising fourth year at UChicago and the co-president of UC Quantum. He's majoring in physics and math and has done research on symmetry protected topological phases in the context measurement based quantum state preparation. For the summer, he has been working in the Michael Levins group on the bifurcation of entanglement renormalization group transformation flow on fractal models. So let's please welcome him to present.
Thanks, Hanyan, for the introduction. Um, and just want to make sure. Can you guys all see my screen? Okay,
Yeah,
awesome.
good.
Um, cool. So yeah, thanks again so much for the wonderful introduction, Hanyan. And today I'll be discussing fracton phases of matter and fracton models. And so the two papers that I'm referencing are the ones in these links, and both of them discuss sort of the fundamentals of fracton phases of matter and what we can study about them. So we'll get started. So first, I want to talk about sort of the motivation, which is that we can get very interesting emergent phenomena from many body quantum systems, and particularly from many body entanglement. So you can have entangled states of matter that exhibit various phenomena, including um, sort of very interesting correlations or collective fluctuations, or new types of quasi-particles such as anyons and Goldstone modes. And for the most popular topic are these exotic qualitative distinct behaviors, which are these quantum phases of matter. And in particular, the quantum phases of matter that probably most people are interested in this sort of intersection of quantum information theory and condensed matter theory are these topological phases of matter. And this has been sort of the new buzzword nowadays. And what does it actually like? What do we actually mean when we say topological phases of matter? Topological, there's so much like topology, right? And so I'll just set sort of a straightforward definition here, and then we'll talk about sort of examples of these. And so when one says topological phase of matter, we're usually talking about two-dimensional lattice models where qubits are living on these like edges or links or the vertices of this lattice. And we are concerned with the ground states of these quantum many-body Hamiltonians that have an energy gap and is made up of local interaction terms. So what I mean by that is if you were to take the ground state and then look at all of the other excited states, there is a finite energy gap between, I wonder if this, um, there's like a laser thing that I could do. Yo, awesome. So there's an energy gap between the ground state and all of the excited states in the energy spectrum. That's what we mean. And this holds in the thermodynamic limit, which is to say that if we take the system size to infinity, we can like make it larger and larger. This energy gap will still persist. And secondly, we define which phases are equivalent to each other by saying that two Hamiltonians, or the ground states of the Hamiltonians, are in the same phase of matter when you can connect them using a smooth continuous path of Hamiltonians, which we can refer to as an adiabatic path. And in the perspective of quantum information, we call them finite depth quantum circuits or finite depth local unitary circuits. So that's how we can talk about whether two models are in the same phase of matter. So what is a paradigmatic example of topological phase of matter? Well, that is the Z2 torque code. And so the Z2 torque code is an example of topological phase of matter, which people say exhibits what is referred to as topological order. And sort of the signatures of topological order include long-range entanglements, which I guess colloquially speaking, you can say that there is a sort of a long-range distance where you can have these non-trivial correlations between qubits. And the other thing is that they have a ground state degeneracy when you choose to define these lattices on non-trivial manifolds, such as a torus. So if you take something like the torque code and you define it on a donut, then you get this like this non-trivial ground state degeneracy. In the case of the torque code, it's 4. And these degenerate ground states cannot be distinguished by local observables, by measurement of local observables. In other words, we have to make measurement of the entire global structure or the topological structure in order to detect these phases of matter that exhibit topological order. And the most sort of the main signature of what is considered topological order is that they host these quasi-particle excitations called anyons or anyonic excitations, which are sort of known to have non-trivial braiding phases. So if you like take two and you braid one around each other, then you can get all sorts of phases. You can get -1, or you can also get I, or you can get anything in between -1 and 1. So this is a signature of topological order. And so real quick, the toric code is defined by these local interaction terms where AV is, we're looking in the context of spin Z eigenbasis. You have these qubits on these little nodes, and the interaction terms are a bunch of these star or vertex operators, which are a tensor product of Pauli Z's, and then you have a plaquette, which is a tensor product of Pauli X's, which you have here. And so it's just a sum of all these local interaction terms or stabilizers, as we also refer to them. Now, they have this property. The toric code has this property where because all of these terms they commute with each other, which means that we can simultaneously diagonalize the Hamiltonian, and so we can represent the entire spectrum of the eigenstates using the individual eigenvalues of every local term. And so the ground state is the simultaneous +1 eigenstate of all these vertex and plaquette operators. And so you can sort of describe the ground state like this using the eigenvalues. So the AV is the eigenvalue of the vertex operator, BP the eigenvalue of this plaquette operator. And on the other hand, we get excited states when one of the eigenvalues attains a -1, which is to say that it is a violation of one of these local interaction terms. And we can also sort of visually think about this as this equal weight superposition of all these sort of loop-like configurations, where you would imagine like you can have like loops like this, like loops here, loops like this, and they all contribute to the ground state. And this is what some people refer to as a string-like condensate or loop condensate. So that is the ground state of the toric code. Right. So to move on to these anion excitations, you can have violations of these vertex and plaquette operators by either having Pauli X's or Pauli Z's acting on these qubits. And if you guys don't understand how these quasi-particle excitations can arise, then I'll try to explain that in a little bit more detail in the next slide. But the idea is that you can have these like string-like operators that produce these quasi-particle excitations at the endpoints. And what is sort of significant about these is that these are flexible. So I can take this and I can add another Pauli X like this. So you have like a longer string operator, and then you have like an anion excitation here, and then you have an anion excitation here, or you can like take this part and you can just like stretch it like this, and then so you have like an anion here, and then oh my goodness, you have an anion here and you have an anion here. So they're flexible. So you can sort of stretch and deform these paths, and as long as the endpoints are the same, it doesn't matter which path you choose to create these anionic excitations. And so in the context of sort of quantum error correction, because these strings are flexible or deformable, it means that these sort of errors are mobile, and so they can propagate throughout the system more easily. And so when I say violation, what I mean is that some interaction term of the Hamiltonian, which can be minimized by some kind of global ground state, it has some other eigenstate such that if you apply that same interaction term onto the eigenstate, then you no longer get the minimum energy. So it corresponds to an excited state of the system. So for instance, we have a Pauli X, and then this AV1 you can imagine as like a star operator where you have Z's on each of the edges. And you should notice that this anti-commutes with the Pauli X if there's like a Pauli X here or just like here, because Pauli Z and Pauli X anti-commute. And so what happens is, and another thing to mention is this omega here denotes the ground state. So if I apply this star operator, then I just get back just the ground state. And so what happens is that if I take this expression here, right, which is equal to this one, then you can sort of put the parentheses around and switch the negative sign to observe that if I act a vertex operator with this, which is the ground state being acted on with a Pauli X, then you get a -1, which is to say that this entire thing is an eigenstate of this vertex or star operator, but it has an eigenenergy that does not correspond to a minimum energy. It corresponds to a non-minimum energy. So you have this excited state right here, where one of the vertex terms are violated, and you have a -1 energy eigenenergy. So now here's things. This is when things get actually very strange, right? So if you add one extra spatial dimension, so now you're working in three-dimensional lattice models instead of two-dimensional, you get this very strange quasi-particle excitations that are called fracton or fracton excitations. So what are they? They are emergent topological quasi-particle excitations, point-like, in a specifically three-dimensional lattice that has this notion of constrained mobility. And it includes not being able to move at all to being able to move to a certain extent, or mobility on subdimensional manifolds. And some and so fracton orders, right? They have all of the properties of topological orders, but they have like additional distinguishing features from topological. So one, fractons in particular, when they're by themselves, I guess they get like scared or something. They get so scared that they can't like move or anything. They become immobile when in isolation. But if you give it a friend, they're like, oh wow, it's a friend, and they can actually start moving together, and so they can often move by forming these bound states or these dipoles. And in addition to that, it has non-string-like operators. So I just want to recap here real quick. If I go back here, these are string-like. These are string-like operators, and these string-like operators are used to create these anionic excitations. But for fractons, there's just sort of strange cases where that is not the case. And then thirdly, they have a robust ground state degeneracy, again, on non-trivial topological manifolds that scales with the system size. So unlike topological order models such as the toric code, the more you make the system bigger, you get a higher the ground state degeneracy. It scales exponentially, and so that's part of the reason why it's an excellent potential platform for something like quantum memory, these fracton phases of matter. So let's talk about sort of the paradigmatic fractal model, which is the XQ model. And so you can sort of think of this as like a three-dimensional generalization of the toric code, where this is like sort of the plaquette operator, but now it's on a cube instead, and these are like the star operators, but you have them on all axes, all three axes, and you can also just sort of represent them like this symbolic form. And here the ground state degeneracy grows exponentially uh, with this sort of parameter, where Lx, Ly, and Lz are the dimensions of the three-dimensional lattice or the cubic lattice. So here, the qubits live on the links of the qubit lattice. These are again all the stabilizers are all self-commuting. They all commute with one another, so they're exactly solvable. So you can represent all of the energy eigenstates or the spectrum using just the eigenvalues of these local interaction terms. These guys, okay, so this is kind of strange. So the XQ model, it hosts fractons, but also hosts linons and planons, which I'll talk about what they are in a second. And they have rigid string-like operators, and then they have membrane operators, which are sort of the non-string-like operators. So what do I mean by fractons, linons, and planons? Well, uh, so you can have sort of various fracton excitations. I think honestly the word fracton, like you see in the diagram here, is sort of strange. I think it should be called a pointon, because there's nothing like it's like fractional in the sense that you need more fractons to be able to move them freely around. But it's just a history of seeing these like fractal structures that people sort of gave it the name fracton. But I think it should be pointon because they can't move. Linons are sort of these excitations that can move along a line. So I mean linons, and then planons because they can move along a plane. And sort of a big issue with these fracton phases is that we don't know how to classify them. We just generally don't know. We've definitely made a lot more progress than the last years. But sort of the main two models that people refer to are type 2 fracton models, where all the excitations of the model are fractons, and type 1 are not type 2. So they can have these linons and planons. So let's talk about the linons of the XQ model. So if you look back here, I'm going to be looking at specifically this guy and then this guy, right? So if I have a Pauli X, this Pauli X violates both this cross term, because this is made of all Pauli Z's, and it also violates this cross term because it's all made of Pauli Z's as well. And so what you end up getting is that this one Pauli Xj can violate the vertex term on this side and this side, as well as this one and this one. And so you end up with two quasi-particle excitations that can move along a line like this. So it can strictly move along a line. Uh, but the reason why we call them rigid is because when we start to introduce these sort of cuts or bends, then you can't really move them freely, because when you try to go up and then make a turn, then you leave behind another quasi-particle excitation, which you don't want. And unlike the flexible string operators for the toric code, the path actually does matter. So you'll notice both of these have the same endpoints, but because they have different paths, you have different additional line-on excitations that get sort of left behind. And so these are not flexible; these are rigid. And so these can move along a line like this. Um, then on the other hand, we have the fractons of the XQ model, and these are violations of the cube term. And so you can have sort of this group of Pauli Z operators that act on the lattice in this way, and that ends up violating these four cube terms. And so each single cube term violation is a fracton, and the red links correspond to a Pauli Z. And so you can sort of take this together and you look at it as a single membrane. And so these are referred to as a membrane operator, which are sort of non-string-like operators. And you can also look at this membrane operator in the dual lattice picture, where you can sort of think about replacing where these red links are with cubes and replacing where each of these cubes are with links. And so you can have this nice membrane picture where you have on each corner a fracton excitation. And these guys cannot move at all. If you just had one by itself, there's no way for it to move, because as soon as it would move, it would just disperse and leave behind a bunch of other excitations. Now we can make this membrane operator, like we can make it bigger. We can make it bigger, and when we make it bigger, these fracton excitations would also appear on the corners of the larger membrane. And so they can kind of move when there's other guys, but when there's only one fracton, then it is completely immobile, which is very strange. Um, but what's kind of cool is if you have two line-ons or two fractons, then there is a flexible string operator for line-on dipoles, where you can apply uh, actually, so line-on dipoles, it should be these guys. It should be these guys. I'm not sure why it's switched. Line-on dipoles, we're looking over here. And so these are all made up of Pauli X's, and then you also have a Pauli X here. And so you can use this to actually move line-ons around in one additional direction. And so it actually becomes a planon, because it can now move in two directions. In other words, it can move along a plane. And you can do the same thing with fracton dipoles, where you can have sort of this additional structure, and you can sort of move these around. And these are called ribbon operators because they kind of look like a ribbon, and there's just sort of a narrower version of these membrane operators. That's the XQ model. And then now a more stranger fractal model is this model called the Sierpinski prism model, or sometimes referred to as the Sierpinski fractal spin liquid. Looks pretty much like the toric code, but the terms look very different. So here the qubits live on these XY plaquettes, and what I mean by XY plaquettes are, I mean by just the elementary squares of the cubic lattice, where it's parallel to the XY plane, and then they also live on just the links that are the z-axis or the z-links. And I'll explain what I mean by tessellated with triangles. But this guy is strange because one, it only hosts line-ons. There's no fractons or planons. And these are generated by rigid string operators. And this guy is sort of the main sort of attraction for today, these fractal operators. And there's some other things about it, such as how it exhibits this self-duality, like the toric code, which is to say that if you took this model and you looked at it in the dual lattice, then you get back the exact same Hamiltonian. You get the exact same physics. And I should also mention it's a self-duality up to a spatial inversion. So it's not completely a self-duality, but it's pretty much one. And then it has these fractal geometries, which I'll talk about, and it's introduced by Benny Yoshida in 2013. And so the violations of AV and BP give you these E line-ons and M line-ons, and they're just sort of labels. The E's and M's sort of come from this electromagnetic gauge theory formalism, which we don't need to talk about. But you get these like line-ons that go along the Z-axis. And here's what's strange. So you can apply sort of like these guys. You can apply these like rigid line-ons for this specifically along the Z direction to produce these line-on excitations. But on the other hand, you can produce them by applying a fractal-like operator that has fractal support. And here's what I mean. So first, this is looking at it from the XY plane. So you're just looking at it from above, and you have these squares, but you can actually separate. This is just for convenience. It doesn't actually do anything physically. But if you divide each cell using like this line where you have this like right triangle, and we say that the qubits now live on specifically these shaded triangles, right? What ends up happening is then we can define these operators like this. And it turns out that if you want to excite the model, specifically these guys, then you can sort of arrange them in a fractal geometric configuration where the line-on excitations appear at the endpoints. And the larger I make this triangle, the more and more it becomes more like a Sierpinski triangle, which is really strange. And you can have like not only Sierpinski triangles, but there's other more generalized fractal spin liquid models which have like weird fractals, which I'll show you guys pictures of maybe at the end, which because they look really strange. They're very but anyways, and these green dots are line-on excitations, and this fracton or fractal-like operator is a tensor product of the Pauli axis. um, right, to violate these guys, actually, sorry, to violate these ones. We were violating the BP terms when it comes to these fractal support operators. So another weird thing is that it's an example of what is called a fractal spin liquid, which is anything. It's a fractal spin liquid is essentially, you can think of it as a non-spontaneously symmetry breaking system with a gap in the energy, where you have these sort of fractal geometry structures. So for instance, or to explain more specifically, the Tor code is just condensate of string-like objects, but here you have, I couldn't find a picture online, so I just had to draw it. Actually, all of these I couldn't find online, so I had to just draw it on the chalkboard. But it's a condensate of like fractal-like objects, and so the higher up you go, the more like sort of Sierpinski triangle-like objects you get. And so in a more formal sense, topological order, they're described by these topological quantum field theories, which we know a lot about. But when it comes to these fractal spin liquids or these fracton models, they cannot encapsulate sort of the many strange ramifications that come from this constrained notion of constrained mobility. So you need to sort of look into the field of homological algebras, and you need sort of more exotic mathematical structures as well, such as using sort of these like chain complexes of finitely generated group ring modules over a polynomial ring, but you don't have to. That's just another thing on its own. But this is to say that they have very strange mathematical structures as well. And so finally, we get to the Haas code, which I think is probably still the most least understood fractal model, and it's introduced by Zhangwan Ha in 2011. And so it has this 8-body interaction term. So the Hamiltonian is the sum of all these guys and these guys. And what this is if I go over here, I can sort of take each component of a term and I can sort of group them together into unit cells. So each unit cell is made of 2 qubits. And when you do that, you can sort of represent them using this notation. And it turns out you can do this for the Haas code, and you end up getting this weird 8-body interaction term. These only host fractons, and the excitation operator boasts a fractal-like geometry, which is like this weird 3-dimensional Sierpinski triangle pyramid prism thing, and where you have these fractons at the corners. And you can make this this operator bigger, and you would have these fractons at the endpoints, but besides that, they can't move. And what's interesting is that this is actually one of the most more original Fracton models to be introduced. And these, like the first Sierpinski prism model and the XQ model, were models that came afterwards to try to understand what Fracton models are like. And they're sort of a simplified version of this weird example, which is really cool. So the conclusion is it's an excellent platform for these future quantum memory hard drives because of these. One is the ground state degeneracy scales with system size, which is super nice because that means you can encode more logical qubits as the system grows with size. But these exotic fractal structure means that if you wanted an error to propagate throughout the system, then they would have to do that in a way where the local perturbations form this fractal like support, this fractal geometry, which is very difficult because it's like a very particular specific configuration. Um, um, and it has a lot of fascinating physics, localization, and you need to sort of go onto either like homological algebra or higher tensor gauge theories, which I say like simply like you know how like ENM, right? ENM it's described by a vector field, where you have like vectors on each sort of point in the field, in the force field. And you can use that. You can use the same sort of structure to describe things like the toric code, and you can describe it as this lattice gauge theory. Um, but on the other hand, when it comes to these fractons, that no longer holds, and you need to move on to higher dimensional structures such as tensors to describe sort of the fracton physics. And unfortunately, there's no actual material that is yet known to exhibit fractons. But if the next model gives more precise indications of seeing what the crystal structure is like or the magnetic interaction should be like, then maybe the experimentalists, such as you guys, some of you guys in the audience, could start designing and measuring such materials, which would be absolutely huge for the program. So yeah, thank you guys so much for listening, and feel free to drop any questions. Thanks, guys. I think I didn't go too much over time.
Okay, I have a question about the manifolds. So, how is the logical operators defined in those like three-dimensional codes? Because I cannot imagine like how to define like logical operations there.
Yeah, right. It's a great question. The logical operators are these fractal like fractal supported operators for some of them. For these guys, for such as like the XQ model, actually, I might have to check on what I just said about the logical operators for these fractal spin liquids. Um, but I believe they should have these like sort of fractal supports. Um, but if that's not the case, that might not be the case. But that's a great point. I should look into that. But for things like the XQ model, instead of having like sort of Wilson loops or these like loops of operators for these logical operations, you would have like sort of three-dimensional like prisms that would like so if you have like a anion, you can have like a Wilson loop like around the torus, they would act as like the logical X and Z. But for these XQ models, you would have like prisms that surrounds these fracton like excitations, which would have to encapsulate sort of the topological or the global structure of these fracton models or the manifolds that these fracton models are defined on. But let me just think about that. How do I, in terms of these fractal spin liquids? Um,
Excitation operators are non-logical operators.
they're not logical
Yeah, they are
operators.
non-logical operators.
Yeah. Okay. Honestly, that makes sense. The operators with fractal support can either be like a symmetry of the Hamiltonian, or they can use they can be used for excitations. But yeah, now that I think about it, I guess it doesn't make sense for them to have. That's actually really frustrating. It's actually really.
Because if you're going to classify the ground state degeneracy.GSD, then you have to classify them by the eigenvalues of the logical operators.
Right. So it is some kind of tensor product of the stabilizers. It's just right. It wouldn't necessarily. Yeah. You know what? I think even for these fractal spin liquids, even for these kind of guys, I think if you wanted to detect like a fracton at an endpoint, then you need some like large like three-dimensional frame.
Yeah, right.
Or I guess in the literature people refer to them as detectors. But I wonder how that would look like though, because you're like it's defined on a much stranger lattice or geometry, and also where the qubits live, not everywhere, but they just live on some places. But I'll think about that and I'll get back to you on that in the next couple of days. Um,
Okay.
yeah. Thanks for the question.
Yeah. Honestly, like it's very hard to imagine like three-dimensional like geometries for logical operations there.
Yeah.
And it would be like insanely hard to decode them. So I guess it's kind of
Right.
yeah.
Yeah.
So maybe using them for error correction will be like unfeasible.
Error correction, yeah, maybe not the best, but for like,
The storing
for,
memory.
yeah, for memory, um, it will be good. Um, yeah, was there another question? I don't know how to access the chat. How do I access the chat from here? Chat, okay, nice. Um, okay. Can you share the links to the two papers you mentioned at the beginning? Okay, for sure. And then even if you don't have a material that exhibits these properties, could we construct a similar code from building up from Pallius, for example? Um, I'm not sure if that because you need so for the fracton physics to emerge, you need these sort of strange geometric constraints. So I'm not sure. I think you would need to find a material, or I guess, yeah, we would have to artificially create one. There's one candidate for spin liquids, which is a mineral called herbertsmite, herbert herbertsmatite. Um, but even that is not known. Right. And then were there any other? Okay. Um.
I have a quick question. Yeah.
Oh,
So, first of all, thank you for adding another word into my lexicon I can use to sound smart. So, yeah, I have a quick question over about the properties of these fractal codes, I guess. So, how does the code distance, I guess, scale with the size of these fractal codes?
no, how do the fractal they all these fractal codes or the fractal models um they all have ground state degeneracy that also scales exponentially. Um and I guess it doesn't seem so intuitive that that would happen. One let's see. There's many ways of going about it. Um but the one that I know is it turns out that you can describe these fractals using Laurent polynomials, and these Laurent polynomials have algebraic geometric properties where you can sort of represent the same sort of fractal configuration, but sort of different variations of the fractal, different variations of the Laurent polynomials, and so you can sort of develop this degeneracy from the structure of these Laurent polynomials that underlie these fractal operators. Um, I guess it just comes out. Mm, let me try to maybe I'm trying to think of a maybe better answer because that right. Why would hmm. Yeah, I mean you can find the ground state degeneracy by taking like I guess in these fractal models, you can do like 2 to the number of qubits minus the number of independent Hamiltonian stabilizers, which like has a relationship with the order of the symmetry group of the subsystem symmetries of these models, and that leads to this 2 to the Lx plus Ly plus Lz minus some kind of scaling factor or some correction factor. Um, um, but yeah, I if I can think of a better, more intuitive explanation, I'll definitely let you know in the next couple days.
So if I want to make one of these, and I have no idea how. Like, it just needs to have the same topological properties, I guess. If I were to try to make one artificially, like the toric code.
Right. I guess if you wanted to make this experimentally, then what the most feasible starting point would be to start with spin liquids, where you have like, even when you're trying to get to the ground state, you have like these frustration interactions, where the entire Hamiltonian is no longer frustration free because if you have like a certain geometry that restricts the qubits to be all aligning the same way, it's like one of them has to be down. And so these, you can start off with those kind of materials, and then from there, I guess you would have to sort of extend that into 3 spatial dimensions, but that's I'm not sure how that would, because you would have like
Yeah.
things aligning like on the plane, but then if you have more on the top, then the top ones would influence the ones on the bottom, and it would be a whole mess.
Yeah, I guess it could be like a cool side project I can do as a hobby.
That's what I'm saying. Just like something light, something calm. Oh yeah, Shrimai, I think I saw your hand.
No, yeah, I was just about to comment on what, like, your question about the spin liquids. Yeah, a lot of people look into like 2D heterostructures and like Moire materials potentially for like you were talking about that influenced by another dimension with the spin frustration. But yeah, we haven't even realized like quantum spin liquids in general, like materially. So I think fractal spin liquids are far in our future, but definitely something. Yeah.
So that's a great. Thanks for the comment, Shrimai. It's a good point. Um, yeah, I'm like just searching up on the literature about like what the logical operators would be for these like more exotic fracton models. And then oh yeah, and I just want to show you guys this really quick. I'll be super fast because I know you guys it's taking up some time. But so I was saying earlier that you can, oh my goodness, it's like crashing. You can use these polynomials to generate these fractals. Uh, sorry. Oh, there it is. And so what we can do is you can actually, so this is like a note documentation that I've been writing for the research project. This is just the Sierpinski triangle is generated by this polynomial here. But it turns out that you can have more strange polynomials and you get these more strange fractals. And these fractals would be like they would theoretically serve as the symmetry or excitation operators, or the structure of those operators for more generalized fractal spin liquids. But you can also have these sort of weird fractals where, I mean, this one is not even a fractal. It's just like this. It's not fractal like. It's just chaotic. It's chaotic behavior. And then you can have sort of these weird guys. And so like each term here would actually correspond to an interaction term in the Hamiltonian. Each one can correspond to an interaction term in the Hamiltonian. And sort of the research that I'm studying is if you have these like sort of generalized fractal spin liquids that are based on these sort of Laurent polynomials, and what can you get is sort of, and what is the entanglement structure after you apply some kind of entanglement RG transformation. But that's what I'm looking at. You can have these weird guys, and this it's like a bunch of faces. Like, anyways.
So wait, so when you code these things, do you just like cut off part of the terms in the ground state? Because I think you mentioned earlier how there's like an infinite expansion of like sum of states the ground state can be decomposed into. So when you actually code these things, like, how do you approximate the actual ground state?
Yeah, that's a good question. I guess it would have to be, well, so the way I coded this was these are taking I take these polynomials and I raise them specifically to this power, to the 2 to the nth minus 1. So it has finite support. So that doesn't go into the sort of infinite dimensional case. But it turns out that if you raise these polynomials specifically at this number, that's when you start getting these weird fractal like geometries. And it has to do with, again, sort of an algebraic geometric fact about, or I guess it's just more more of a fact of Laurent polynomials over a finite field. It's called the freshman's dream. It's like sort of the main theorem that can be used to explain why you get these guys, like these like discrete scale symmetries. But right. I'm not sure if I actually answered your question, to be honest. Because you were.
Yeah, I think I was like referring to the fractal codes, I guess, the
Oh,
Hamiltonian.
fractal codes. I see.
Yeah.
Oh,
So,
oh.
like, what term? When do you like stop adding the terms, or do you like?
Yeah, you just like, I guess. So the ground state subspace is generated by the stabilizers in the Hamiltonian, and the number of stabilizers or the Hamiltonian terms would be like 2 to the n number of terms. Like you just stop at like 2 to the n minus 1. That's what I meant to say earlier. I'm not sure if does that make sense?
Yeah, I guess. So you like generally you just need all of the terms, or can you like, for
Yeah,
example, suppose my computer is smoking. When if I added all the terms, would it be appropriate to like stop halfway and just call it a day?
you can stop halfway. Like you can like, okay, so you can, I guess you can have a Hamiltonian where it's like you can start off with like a Hamiltonian. So essentially this is what this is doing. I'll be okay, I'll be super fast about this because I have a chalkboard here, so I can just talk about this really quick. I'll be super fast. Okay. Not sure if you can see that. Okay. So right, if you have the following polynomial 1 plus x plus y, like this, then this corresponds to putting a qubit. So 1 corresponds to putting a qubit at 0, 0. X corresponds to putting a qubit at 1, 0. It's like the x coordinate is 1. And then y corresponds to putting the qubit at like 0, 1. And if you had like x squared y cubed, then this would correspond to putting a qubit on 2, 3. But essentially, you can use these polynomials to describe sort of like how these interaction terms are defined. And if I were to sort of put this in terms of dots, then I would have like a dot here, where actually people do like f bar, which is like a spatial involution of this. So you would now have a 1 plus x to the minus 1, 1 plus y to the minus y to the minus 1. So you have like qubit at 0, 0, and then you have a qubit at like negative 1, 0, and then you have a qubit at negative 1, 0, negative 1. And then so you can define the Hamiltonian as the sum where the interaction terms are defined by having tau z's up on top of each of these points that you define using this polynomial. And then what you would end up having is that you would like sort of take powers of f. And when you take powers of f, then obviously you get many more terms. You get a lot more terms. And then that would correspond to sort of how many interaction terms there are. But it's more that the Hamiltonian doesn't necessarily need to have a lot of terms. It could be like 1 plus x plus y, and that would just be a 3-body term. But when it comes to the excitation operators, that's when you have a bunch of these guys. But the issue is if you want to create Fracton excitations at the endpoints, then you need like probably 1,000, 10,000, 100,000 qubits. I mean, because it scales like exponentially. Um, um,
So I
but
need to call up like Jensen Huang for a new GPU, I guess.
yeah, exactly. We might have to collab with Mr. Huang himself. Um,
I think he's a little busy, but it's worth a try.
we could do like UChicago, QISCA, reach out together,
That would be awesome.
get a response. Um,
I'm actually reaching out to a lot of US universities and US like consortiums like the QEDC, but they
when you
generally
say
do not
yeah,
respond or either state that they're only for the United States.
I see. No, you should keep reaching out though for sure. Should
Yeah,
keep reaching.
definitely.
Yeah. Anyways, that's okay. I think I've taken enough time. Thanks for the questions.
Can I ask one last question?
Yeah.
If we were to make a quantum memory with this uh, Fracton model, then what would be the encoding rate of this model, and how will it depend on this geometry?
Mm, are you when you say encoding rate, are you talking about
The
the
number of qubits,
number of
then, and
qubits?
yeah.
Okay. Right. Yeah, I guess it really just depends on the fractal model. Like the XQ model is not like it is not a model. It's like it's a paradigmatic example of studying fractal models, but it's not one that we would want to use to create like quantum memory. It would be more like Haas code that we would want to use for quantum memory. And so for that, you would um yeah. I suppose you have the Haas code is defined on a qubit lattice where you have like you have pairs of qubits living on each vertex of the cubic lattice in a certain sense. I can't give you a quantitative answer off the top of my head, but I think it would just it would scale pretty fast as the system grows with size. Though I guess the advantage of that is that once you can do that, then you can encode a lot of logical qubits as a result. Um, but yeah, I'll say that for now.
Okay, thank you.
Of course.
So could it outnumber the number of qubits that are used to make that memory then? The interaction encode additional information.
Oh, oh. Honestly, maybe. Yeah, they're like 8-body interaction terms too. So, hmm. Yeah, maybe. It's a good point. I'm not sure though.
Thank you.
Of course. Thank you.
So I guess that's it for the presentations if there aren't any more questions.